Okay, this is number 4 from the 2010 Form B AP Physics B exam, and we're looking at a circuits problem with a little bit of EM tossed in there. And we've got our circuit, EMF is provided, we've got resistors R1 and resistors R2, and we've got a point P referenced here. We're going to need to answer everything in terms of the variables given and any fundamental constants. And then we want to first derive an expression for the total resistance of the circuit. So really what you got to do is address your parallel branches first, and then within parallel branches address any series branches, but we don't have any of that. So I see a parallel part right here, so I want to resolve this part first. I want to create equivalent resistance for the parallel. So I'm going to say 1 over my parallel, which I think I'll just indicate as 1 over R with parallel lines. You could maybe write 1 over A or 1 over P to represent parallel, anything like that, will equal 1 over R2 plus 1 over R2. And since the bottom number for each are the same, we're looking at 2 over R2. However, that's 1 over the parallel equivalence. So we don't want 1 over parallel anymore. We want parallel. So my parallel equivalence is going to be R2 over 2. Now at that point, my overall equivalence, my total, or whatever, what I'm looking for, will be everything in series. We'll have R1 in series with that branch we just found, in series with R1 again. So R1 and R1 will add together, so I'll have 2R1 plus that branch we just determined, R2 over 2. That is the answer for A. Pay attention to your, just make sure you're not changing the subscript randomly or anything, because they have to be in terms of the variables and terms given, and that was R1 and R2. B wants us to derive an expression for the power dissipated in the circuit. Well, there's a bunch of equations for power, but the one that you're going to be using here is going to be V squared over R, or in this example, V is written as EMF, so it'll be the EMF squared over the R equivalence. You could write over R total, but that would be not completely right because that's not one of your algebraic givens. So we have to use this value for my R total. So we're going to say EMF squared divided by quantity 2R1 plus R2 over 2. And there it is. Now we're going to assume that the magnetic fields created are only from the 2 long wires. And we want to know what is the direction of the magnetic field at any point at point P, or not at any point, if any, at point P. So we have positive terminal here, negative terminal here, which means we have positive current flow to the right. All the way down here, we have positive current flow to the left. So we have to address the field created by both of these wires independently. The top wire, you're going to use right-hand rule where you take your thumb and point it in the direction of the current, and you're going to wrap your fingers around that wire. So that top wire, if you wrap it far enough down, will have and I'll do this one in red, all the way down this bottom half, everywhere down here, the field will be into the page. So that would be represented by X's. All the way around, let's do the top wire. I'll do the blue, the bottom wire in blue. The bottom wire, its current is in the other direction, so you're going to take your finger pointed to the left, and your fingers will wrap around, and underneath the wire, they're going to be coming right out towards you. So the bottom wire has field lines coming out towards us, right? Now, because they're not going to be equal because one primary reason. The current in each are the same, but point P is much closer to this bottom wire. So the strength of the field that's into the page, out of the page, will be significantly stronger than the field into the page. So that one's going to win, and they're vectors. So ultimately, the net direction of field will be out of the plane of the page. And use the right-hand rules and all that thinking I said out loud in your explaining. Then D, we want to know the direction of the force, if any, of the bottom wire to the top wire. I think this is easiest to remember the parallel or anti-parallel rule. In this example, the current in these 2 wires will exert a force on each other. They're either going to repel each other or they're going to attract each other. And if the wire current are parallel, meaning they're in the same direction, then they're going to be attractive. If they're anti-parallel, meaning one's in one direction, the other's in the other direction, they're going to be repulsive. So right away, I already know this bottom wire, it's going to experience a force downward. However, you could also use your right-hand rules to determine that. Remember, the top wire has its field by these red X's representing into the page, right? That means this wire, which is now in a field into the page to the top wire, you can use another right-hand rule in that to figure out the direction of force. And that's the right-hand rule where you take your index finger, you put it in the direction of the force, of the current through the wire. you're going to take your remaining fingers and put them in the direction of the field, and your thumb, which is perpendicular to all the others, will be pointing in the direction of the net force, which at that point would be pointing down. Either way, you should be able to explain it from either direction you take, and that should be completely appropriate. Okay, that completes this problem. Thank you.